Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now I'm just going to get started on our set of questions for today's session. Okay, so question 1 asks, what mass of water at 25 degrees Celsius must be allowed to come to thermal equilibrium with a 1.85 kilogram ice cube or cube of aluminum initially at 150 degrees Celsius to lower the temperature of the aluminum to 65 degrees Celsius. Assume any water turned to steam subsequently condenses. Okay, so this question gives us a lot of different variables that will help us answer the question. So they give us the mass of aluminum. So it's an aluminum cube that weighs 1.85 kilograms. But I will convert this to grams. So 1,850 grams. They also give us the initial temperature for aluminum. So T initial for aluminum is equal to 150 degrees. And T final of aluminum is equal to 65 degrees. And they also give us the T initial of water, I believe. What mass of water at 25 degrees must be allowed to come to... Yeah, I'm not sure whether this would be the 25 degrees as the initial or the final temperature of water, so I'm just going to leave that at T. So to answer this question, we would need to use the equation Q equals mc delta T. So C stands for the specific heat capacity. M is the mass and Q is the heat. So in terms of the specific heat capacity, depending on what type of reactant you have, it will vary. So these are values that are given to you, but I will look them up since they aren't given in the question. Okay, so I'll look up the specific heat capacity first of water. So usually this is given to you in the question. So for water, it is 4.184. And then the units are joules per gram times degrees Celsius. So now let's look up the heat capacity of aluminum. So the specific heat capacity of aluminum is 0.900. And it has the same units, joules per gram times degrees Celsius. Okay, so the first thing we need to do is solve for Q. So step 1. Solve for Q, which is also the heat to equilibrate the aluminum temperature. Okay, so to solve for Q, I would just simply need to plug in all the values I had written out up there. So for mass, I converted it to grams. So it's 1,850 grams. The specific heat capacity of aluminum, we looked up and it was the 0.9 joules over grams times degrees Celsius. And delta T is T final minus T initial. So it will be, let's see, -65 degrees minus 150 degrees. Okay, so if we do all the math and try to solve for this, you end up getting negative 141,525 joules. Okay, so this is the heat that is released, and it will be the same with the water as well. So part 2 of this question is to solve for the mass of water. So just using the same equation, Q equals mc delta T, but I am going to rearrange it so that it's M is equal to Q over C delta T. My Q value will just be the heat that I calculated in the first part of the question. But the positive value, the C specific heat capacity of water is 4.184 joules over grams times degrees Celsius. And the delta T is just 65 minus 25. So this gives us a mass of water of 845.6 grams. Or if we wanted to express this in kilograms, it would be 0.846 kilograms. Okay, so let's see what the junior tutor said. Given values, heat capacity of water is 4.184 joules over grams times degrees Celsius, and they have the heat capacity of aluminum to be the 0.900. First, solve for the amount of heat needed to equilibrate aluminum temperature. Okay, and they got the 141,525 joules. Then, using this heat, compute for the amount of needed water. Okay, and they also got 846 grams. So I can say that this solution is correct. Okay, moving on to question 2. The enthalpy of vaporization for acetone is 32 kilojoules per mole. The normal boiling point for acetone is 56.5 degrees Celsius. What is the vapor pressure of acetone at 23.5 degrees Celsius? So to answer this question, we would need to use the Clapeyron equation. So basically, it can be summed up as ln of P2 over P1 is equal to the delta H of vaporization over R, which is multiplied by 1 over T1 minus 1 over T2. Okay, so let's look at all the values that they gave us. So R is the gas constant, and it is 8.314 joules over mole times K. So T1 in this question would be the 23.5 degrees Celsius. So I'm going to convert this to Kelvin since I want it in the same units as my R. So converting this to Kelvin would be 296.15 Kelvin. T2 for this question would be the boiling point of acetone, which is the 56.5 degrees Celsius. And again, I'm going to convert to Kelvin by adding 273.15 to get 329.65 Kelvin. Okay, so we also are given the enthalpy of vaporization. So this is the delta H vap, which is 32.0 kilojoules per mole. But again, if you look at my R constant, its value is given in joules, so I'm also going to convert this to joules by multiplying by 1,000. So you end up getting 32,000 joules per mole. Okay, so we are looking for vapor pressure. So P1 is equal to question mark. And we assume this started at standard pressure, which is 760 torr. Okay, so I'll just put in brackets standard pressure. Okay, so now we can put all these values into the equation. So it will be ln 760 torr over P1 is equal to 32,000 joules per mole over R, which is 8.314 joules over mole times K. Then this is multiplied by 1 over T1, which is the 296.15 Kelvin, minus 1 over 329.65 Kelvin. Okay, so now if you plug all these values in to the calculator, you want to make sure you do what is in brackets first. So I would personally do the 1 divided by 296.15 separately, and then minus bracket 1 divided by the 329. And then after solving for that is when I would multiply it by 32,000 and then dividing by the 8.314. Okay, so let's simplify the right side. Plugging that all in should give you 1.321. And to get rid of the ln, we are going to do e to the power of both sides. Don't know what that's like called, but e to the power of 1.321 gets rid of the ln on the left side. So if you were to solve for that, it is 3.75. Then I'll write P1 is equal to 760 torr divided by 3.75, and this gives us a pressure of 202.9 torr. Okay, so let's see what the junior tutor said. Clausius-Clapeyron equation relates the vapor pressure, enthalpy of vaporization, and temperature, where R is equal to the ideal gas constant. If P1 and P2 are the vapor pressures of two temperatures, T1 and T2, the equation takes the form ln P2 over P1 is equal to delta H Vap over R times 1 over T1 minus 1 over T2. Okay, so they also show the conversion to Kelvin for our temperatures. And P2 would be standard temperature, 760 torr. Substituting the values to the formula gives us this. So they did the same approach and ended up getting 202.87 torr. Okay, so the solution is correct. Okay, so now let's move on to question number 3. Okay, so question 3 just asks, what is a bond length? Okay, so as you can guess, bond length is the distance between two atoms. So let's say we had chlorine and this is the bond. Space in between would be the bond length. Can't spell length today. Okay, so let's see what the junior tutor said. Bond length is the measurable distance between two covalently bonded atoms. This measurable distance is an average, as the distance between atoms bounded together can change. Electrostatic forces, where opposites attract, contribute to the strength of a bond. A modified formula of Coulomb's law explains the relationship between bond energy, which is the strength, and bond length. The greater the bond length, the less energy required to break that bond. The shorter the bond length, the more energy required to break the bond. Okay, so they also have steps on how to determine the bond length. 1, draw a Lewis structure. 2, determine of radii in picometers for each atom bonded. 3, sum of total radii. Okay, so this solution is correct. Okay, on to question 4. What is the formula mass of copper sulfate? So formula mass would just be the same thing as molar mass. And to solve for the molar mass of copper sulfate, we need to find out the individual atomic masses of each of these atoms involved. So these are the values that you would find on your periodic table. The molar mass of copper plus the molar mass of sulfur plus 4 times the molar mass of oxygen, since there are 4 atoms of oxygen, will give us the total molar mass of copper sulfate. Okay, so the molar mass of copper is 63.546 grams per mole. The molar mass of sulfur is 32.065 grams per mole. Then I'm going to add 4 times the molar mass of oxygen, which is 15.99 grams per mole. Okay, so if you add all these values up, you end up getting a final molar mass of 159.61 grams per mole. Okay, so let's see what the junior tutor said. Formula mass / molar mass of copper sulfate is 159.61. To calculate for the molar mass of a compound, first let us determine the individual molar mass using the periodic table. Okay, so they showed copper, sulfur, and oxygen's molar masses. Then multiply each by the number of atoms and add all up. Yep. So I can verify that this solution is correct. Okay, so on to question 5. What is the ionic compound formula of sodium sulfate? Okay, so let's look at the name sodium sulfate. So sodium is Na+, so it just has a +1 charge. And in the case of sulfate, it is SO4 2-, so it has a 2- charge. So therefore you can see that we need 2 ions of sodium in order to neutralize the -2 charge of the sulfate. So to write out its ionic compound formula, I'm going to put a subscript of 2 under the sodium to show that we need 2 atoms. And then I'll just have the SO4 brackets. I don't even think you would need the brackets in this case, since we only have 1 atom or 1 ion of SO4. Okay, so let's see what the junior tutor said. The compound sodium sulfate is made up of 2 ions, the sodium ion Na+, and the sulfate ion SO4 2-. Since we already have the chemical symbols for each component of the compound, we will just apply the rule on writing the chemical formula of ionic compounds. A cation A with an oxidation state of +X that combined with an anion B with an oxidation state of -Y will form a chemical formula of AyBx. Cation for this compound is the sodium ion, while the anion is the sulfate. Thus, the chemical formula would be Na2SO4. Yep, so that's a interesting approach. It's pretty much the same thing. So this solution is correct. There we go. Okay. Okay, so question 6 just asks, how do you convert grams to moles? Grams to moles? So grams is a unit of mass, which I'll denote as lowercase m, and moles I'll denote as lowercase n. So to solve for number of moles, it would be mass over molar mass. So molar mass is the value that you would just find on your periodic table, also known as like atomic weight. And its units are in grams per mole. So if a question gives you a mass in grams, if we know the molar mass of the compound, all we would need to do is divide by the molar mass. You'll notice the grams should cancel out, and we are just left with our moles. Okay, so let's see what the junior tutor said. The grams and moles of the sample are related by the molar mass of the sample. In the equation, we have molar mass is equal to mass over moles of sample. Molar mass is the mass of an element / compound present in 1 mole of this element / compound. Molar mass can be found on the periodic table. For compounds, the molar mass is simply the sum of all the molar masses of the elements present in the compound. After identifying the molar mass of the sample, the mass can now be converted to the number of moles using the equation given above via moles of the sample is equal to mass over molar mass. So it is a big factor here to identify first the molar mass of the sample before we can convert it into moles. Yep. So this solution is correct. Okay, so on to question 7. Is sodium hydroxide an acid, base, or salt? So if we write sodium hydroxide and try to separate it into its ions, you get Na plus OH minus. So if we recall the definitions of acids and bases, a base produces OH minus in solution. So therefore, NaOH is a base. In the case of an acid, this produces H plus in solution. So for example, if we had hydrochloric acid, it will produce H plus Cl minus. An example of a salt would be like sodium chloride, which is simply just table salt, actually. Okay, so let's see what the junior tutor said. NaOH is a basic compound. By definition, bases are compounds that produce hydroxide ions, OH-, upon dissociation in water. In the case of sodium hydroxide, it completely dissociates in water, thus we can say that it is a strong base. Yep, so this solution is correct. Okay, so question 8 asks, what is a single displacement reaction? Single displacement reaction. So this is when only one element is replaced by another in a compound. So for example, let's say you had an element A plus a compound BC would make AC plus B. So you can see here that the A and the B just switch spots. And now the A is bonded with the C. So similarly, that's the single displacement reaction. We can also have a double displacement reaction. So I'll write out this example. This is when you have two compounds. Let's say it's AB plus CD. And then when they dissociate into their ions, two of them kind of switch places. So you get like AD plus BC. So if you see here, it's similar to single displacement, except the C and the A kind of switched, and like the B and the D switched. Okay, so that's an example of a double displacement reaction. Okay, so let's see what the junior tutor said. Single displacement reaction is a type of reaction where an atom reacts with a compound, in most cases ionic compounds, and the atom forms a bond with one of the constituent atoms of the compound, leaving one of the constituent atoms of the compound unbonded, hence the name displacement. The reaction is generally written as A plus BC makes AC plus B. As an example, when copper metal reacts with sulfuric acid, H2SO4, it forms copper sulfate, CuSO4, and produces hydrogen gas. Process can be written as copper plus sulfuric acid makes copper sulfate plus H2. As you can see here, the copper bonds with the sulfate ion and displaces hydrogen, resulting in copper sulfate and hydrogen gas. You can see here that the copper and the H2 kind of switch spots. So this solution is correct. Okay, on to question 9. What is a Bronsted acid? So Bronsted has that O. The Bronsted acid is the species that donates a proton. So a proton is the same thing as saying an H+ ion. And I'll also write out the definition of a Bronsted base. As you can guess, it is the opposite of the acid. It is a species that accepts a proton. Okay, so let's write out an example just so that we can label all the species of this reaction. Let's say we had NH3 plus H2O makes the ammonium ion plus a hydroxide ion. If we were to label which ones would be the acids and the bases, you'll notice that the H2O, so the water, is the one that donates one of its protons to the NH3. So this makes the water our Bronsted acid. Since it donated the proton. The NH3 would be the Bronsted base. And then if we were to look at the products that were formed, the ammonium ion is our conjugate acid, and the OH- becomes the conjugate base. So these can also be labeled as another Bronsted acid and Bronsted base. Since if you were to do the reverse of this reaction, the OH- would accept one of the protons and become water, and the NH4+ will give one of the protons to the hydroxide ion. Okay, so let's look at the junior tutor's answer. A Bronsted acid is any species that can donate a proton to another molecule. Okay, so they have an example as well. C6H5OH plus NH2- makes C6H5O- plus NH3. This donates an H+ to NH2-, and thus C6H5OH is the Bronsted acid. Yep. So this solution is correct. Ten just simply asks what is an acid. So this is similar to our previous question. So there's a lot of different definitions of acids. It is an H+ donor. It has a low pH. So like a pH less than 7. Let's see what the junior tutor said. Since there's a lot of different definitions you could have for an acid. So acids by definition are chemical substances that have sour tastes. It turns the litmus paper from blue to red and can react to certain bases to form a salt and promote certain chemical reactions. Substances that are acidic contain one or more hydrogen atoms that are released in the solution as a positively charged hydrogen ion. If we were to review the Arrhenius theory, it defines an acid as any chemical substance that produces protons when dissociated in water. These positively charged hydrogen ions, when combined with water, forms the hydronium ion H3O+. The lower the pH of a concentration, the more protons are present in it. Chemicals that have a lower pH reading are termed as acidic. Yep, so this solution is correct. Great example. Okay, so on to question 11. Just simply asks, what is the aluminum molar mass? So you would just simply find the molar mass of aluminum on the periodic table, and you'll see that it has a value of 26.98 grams per mole. Okay, so the junior tutor said molar mass is the mass of 1 mole of the element. So the molar mass of aluminum is the mass in grams in 1 mole of aluminum. From the periodic table, the molar masses of the elements are given. The molar mass of aluminum is 26.9815 grams per mole. Okay, so this solution is correct. So question 12 just asks, what is the chemical formula of baking soda? So baking soda is a must-have in like kitchens and for cleaning. And its chemical name is called sodium bicarbonate, which is just a white powder. Okay, so if you look at the chemical formula of sodium bicarbonate, it is just NaHCO3. And I can also draw it out just so that we can see what it looks like. We have sodium ion, negatively charged oxygen, and then a carbonyl group attached to that. Okay, so let's read what the junior tutor said. Baking soda, also known as sodium bicarbonate, with an IUPAC name of sodium hydrogen carbonate, is a chemical compound with a formula of NaHCO3. It is a salt formed from the sodium cation Na+, and a bicarbonate ion HCO3-. It is a white solid crystalline, but often appears as a fine powder. Its most common household uses is in baking. Yep, so this solution is correct. Okay, so question 13 just asks, what is the molar mass of iron? Okay, again, you would just simply find iron on the periodic table and find its atomic mass, which is 55.85 grams per mole. Okay, so the junior tutor said, molar mass is the mass in grams or kilograms of 1 mole of units of a substance. For iron, we can look at the periodic table. Representation of this periodic table is shown below. So they show the atomic mass, or the atomic number, sorry, which is on top. It's 26. So this would be the number of protons that are in iron. And the number at the bottom, which is typically, you'll see it has like a decimal located. It's usually the larger value. That would be your molar mass. So they said the number in blue is the molar mass, which is 55.845 grams per mole. So this solution is correct. It's going to give props to their use of the periodic table diagram. This unique answer. Okay, so on to question 14. How do you calculate the concentration from absorbance? Okay, so to help us answer this question, I'm going to talk about the Beer-Lambert law, or the Beer-Lambert equation, which basically just shows that absorption is directly proportional to concentration. So let's say I had a simple graph and I had concentration as my x-axis and absorbance as the y. And if we were to plot the absorbance values of a species that increased in concentration, you'll kind of get something that looks like this. And then if we were to plot this and show the line of best fit, you get a straight line going up. And in simple like terms, when you just have y equals mx plus b, it's basically the same thing. So y, the absorbance, is equal to the slope times just concentration. But for the Beer-Lambert law, our slope has a value as well, and they are just constants. So I'll write out the actual equation here, and then I'll define what all the terms mean. So C, as you can guess, is concentration. And we mentioned A to be absorbance, which is unitless. E is something called molar absorptivity. And the B is the light path length. So this is usually given to you in the question. Sometimes it's just 1 centimeter. Yep, so that is how one would calculate concentration from absorbance. So let's see what the junior tutor said. The Beer-Lambert law, or Beer's law, describes the relationship between the attenuation of light as it traverses a material and the properties of that material. Beer's law shows the linear relationship between the absorbance and the concentration, molar absorption coefficient, and length of the light path of a solution. This is mathematically expressed as A equals molar absorptivity times B times C. Absorbance is unitless because the units of the three other parameters will cancel out. Concentration should be measured in molarity, or moles per liter. Light path is usually reported in centimeters, and the molar absorptivity is usually reported in liters per mole times centimeters. To calculate for concentration from absorbance, 1, if the absorbance, molar absorptivity, and light path are given, we can simply plug in these values in the equation to solve for the concentration. 2, if we are given a set of experimental values of absorbance and concentration, and we need to determine an unknown concentration from a known absorbance, we need to plot the values with the form y equals mx plus b to determine the values of slope and y-intercept. Wow, that was a very formative answer. Okay, so I like how they had a use of having two different scenarios where one needs to calculate for concentration from absorbance. Okay, so question 15 just asks, what is the molar mass of KHP? So KHP isn't like just potassium, hydrogen, and phosphorus put together in a compound. It's actually a short form for a compound called potassium hydrogen phthalate. So it has a chemical formula of C8H5KO4. Okay, so to find the molar mass of KHP, it's going to be 8 times the molar mass of carbon, which you would just find on your periodic table, 5 times the molar mass of hydrogen, since there are 8 carbon atoms and 5 hydrogen atoms in KHP, plus the molar mass of potassium, so we don't need to multiply it by anything since there's only 1 atom of potassium. Lastly, plus 4 times the molar mass of oxygen. So now I'm just going to sub in all of their molar mass values. So carbon has a molar mass of 12.01 grams per mole. Hydrogen has a molar mass of 1.01 grams per mole. Potassium has a molar mass of 39.098 grams per mole. And lastly, oxygen has a molar mass of 15.99 grams per mole. Okay, so if we were to add up all these values, you get a final molar mass of 204.24 grams per mole for KHP. Okay, so let's see what the junior tutor said. KHP is potassium hydrogen phthalate. Its chemical formula C8H5KO4. Molar mass of KHP is equal to 8 times the molar mass of carbon plus 5 times the molar mass of hydrogen plus 1 times the molar mass of potassium plus 4 times the molar mass of oxygen. And they also got 204.236 grams per mole is the molar mass of KHP. Yep, so this solution is correct. Okay, so I think we have time for one more question. Question 16 asks, what is the formula for iron 3 oxide? So when you have a chemical name that has like a Roman numerals in brackets, that shows us that the iron has an oxidation state of +3. So if I were to write these as their ions, it would be Fe 3+, and oxide is just an oxygen anion, and it has a charge of 2-. So we would need 2 atoms of iron and 3 atoms of oxygen. So some people just like to, like, I'll show it as if it was just generally speaking, if I had an element that had a charge of +X and another ion that had a charge of -Y, if these compounds were to come together, the subscript of the first ion would have the same value as the charge of the second ion, and then the second ion, its subscript would have the same value as the charge of the first ion, if that makes sense. So finally, the formula for iron 3 oxide is Fe2O3. Okay, so let's see what the junior tutor said. The iron on the compound given has a charge of 3+ as stated by the Roman numeral number, while the oxide came from the oxygen with a charge of 2- as can be retrieved from the periodic table of elements. Following the rules on constructing the formula of compounds, the charge of the cation will become the subscript of the anion, while the charge of the anion will become the subscript of the cation. We now have a formula for iron 3 oxide as Fe2O3. Yep, so this solution is correct. Okay, so that is all the time we have for today's session. If you like today's Q&A and you'd like to be notified of when we do this next, please hit the notification bell and the subscribe button below. If you'd like to submit a question of your own, then check out the links in the description. Also, if you like today's video, go ahead and give it a thumbs up and comment, and don't forget to share with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.